Hello everyone, it's October the 10th. Wow, we're already more than 1 week in October. Time flies. Alright, it's a medium question. So I think now they're doing only one difficult questions per week. Maybe we can do something different. I'll definitely be more willing to do more medium questions. And difficult ones requires time and energy, but medium ones is good for practice. So we'll see. If we got some question that's too easy, we probably will do another one. All right, let's take a look at this one. What we have today. Bitwise AND of numbers range. Didn't mean anything to me. All right, I don't think I've done this before. Nope. Okay, so given two integers, left and right, that represents the range from left to right. Return the bitwise AND of all numbers in this range, inclusive. Oh, this is quite interesting. This is quite interesting. Of course, you cannot do one by one, so you need to find some trick, right? So bitwise AND, and we have values. But apparently, right? If the values have, so we should only care about the values of lowest number of bits, because in this case we have a value have high bits, but you're ending with someone with low bits, so all the high bits gets cancelled. So all we care about is the numbers with the lowest number of bits, which means if you have a left side, then the right side shall be, so whatever the left side is, right? The left side can give you a little bit of value, and then the right side shall be, actually I need to know the number of bits on the left side. So let's say 5. The number of bits on the 5 is 3 bits, right? So the maximum you need to worry about is 3 bits, which is 111, right? Which is 8. Wait, no, that's not 8. That's 7. So it's going to be 1 left shift the number of bits in the left minus 1. That will be the top we need to worry about. Actually, it's going to be the minimum between this value and the right value. So if the right value is smaller, definitely take the right. If the right value is bigger, you take the bigger one. Okay, so when that is in town, then we know the top level. So the right is basically is useless. We get a new value for the right, and then what we do know is, because we're talking about the number of bits, so that the most significant bit will always be 1, and then the range to the higher one will always be 1. So that one's good. So it's going to be 1 something, right? It's going to be 1 something. Now the question is the remainder, the remaining. Will it be all 0? Well, would it be all 0? Well, it's not. I mean, 5 and 7. 5 and 7. 5, what's a 6? 6 is 110, right? And then if you OR them, so as long as there is 1 0 appearing in any position, then we're gonna have 0 along that one. Okay. So the question is, when you start from 1 0 0 something, and then if you go all the way to or 1, they're gonna be 0 at every position, right? So for the starting point, like the starting point, no matter how many ones and zeros we have, and then we have the end point, right? I mean, the end point can be, yeah, it depends on the end point. How do we analyze that? Well, as we get bigger, we'll fit more ones into it. I mean, we can't know, like the starting point, right? We have a starting point, then we know where the zeros are, and we know where the ones are. So all the positions that have 0 will always be 0. So we only need to care about the position with 1, right? Therefore, what we need to know is along the line where we have values in those positions, if there are numbers in those positions that has 0, then we are done, right? So what are we saying? What are we saying is, how do we know if this position is going to be? Well, we do know if we say, like, what's the smallest value that's larger than the left that will have this position become 0, which is we just add that value to it, right? So one left shift this, we add a value to it, and we check if that value is going to be a value within the range. If it's, yeah, because that is the, wait, is that the smallest? Is that the smallest that can make that into a 0? Hold on, let me think. We have a 1, let's say we have a 1 at a certain position, and then the lower end, we start changing, whatever. And then they will change until a certain value that will make this into a 0. So when will they make it into 0? Ah, so the smallest will be, let's say, an example, right? Let's say we have 1, 0, 0, 1, 0, 0, 1, right? So the smallest that would make this into a 0 will be a 1, 0, right? Will be a 1, 0 that will make that into a 0. And then to make this one into a 0, the smallest will be this, right? The smallest will be 1, 0, 0, 0. Therefore, what we can do is, I need to know the value of this, and then compare that to the right, to the limit, and see if this one's in it, right? Because the final value is going to be 1, 0, 0, something we don't know, 0, 0, something we don't know. So we just need to know, can this be maintained? And if we have the smallest value with this 0 is in the range, then this one cannot be maintained. Same with this. So we can go from right, so look for, okay, this is the position we know, and then we need to left shift 1. It's not left shift 1, we just, the base value, right? We have the base value, so 1 left shift this much, the base value, plus 1 left shift this much, and see if that is in the range. And then we'll do the same with this. Okay, I think we have a strategy. All right, let's code it up. All right, let's see. It's this one. I need this one. All right, so this is for today, 10:10. Hold on, this is 10:9. I got that wrong. There we go, this is 10:10. Let me pull it up. So 10:10. All right, so we're going to follow the same idea as we have. So first of all, we need to find the range. So we're going to say the right actual high is going to be minimum of right, and we need to do some stuff first. How do I know? How do I know the number of bits? Well, I can. Is there an easy way to know the number of bits? Well, let me say n, number of bits. Number of bits equals to len, binary left. We're going to call binary left the first time. So binary left equals bin left, and I think 2 to the end, because that's 0b at the beginning, right? So that's the binary left. And then we got a binary left, and high is going to be 1, left shift, len binary left minus 1. I'm pretty sure I need to put parentheses on, right? So this one will give me 1, 1, 1, 1, right? That's the high level, so we pick the smaller between the two. And once we've done that, we have a high, and then we need to do, okay, what do we need to do? We're going to find the lowest value, right? The lowest value that will make this one a 0. Actually, I just realized it's going to be bigger than this, right? Because the lowest value, we say, turn this into 0, we buy, because this one counting up, right? Counting up, so it's always moving forward, so that will be bigger. Okay, that's fine. So what we do is for, I don't know the number of, oh, the right shift. Oh, we can go right shift. The number of times into right shift. So we right shift 1. So we compare this with 1, right? And then as we are right shifting, and we count how many right shifts we do. So that will be the 0 right shift. So we need to do, and then this one will be 1, 2, 3, right? So shift to 1, shift to 2, and then shift to 4. 3, no. How many right shift to reach this one? Right shift once, twice, 3. That's 4 times. I mean, right shift 4 times, right? So right shift once, right shift twice. No, 3 times. 3 right shift. 3 right shift. So we can do a right shift. So I'm going to say low equals left. I don't want to change left. So say while low, right? If low and 1, then what? What is a scheme, man? What is a scheme? Can we just say that position will be kept, right? And if this position is kept and the next position is not kept, so we have a result. So low is left, the result is going to be left. So low starts with left, and while low, I don't even know how many times we left shift. We have the count. We need a count. Oh my god, so many variables. Count is 0, right? So if this, then we know there is a 1 at the current position. Then what we need to do is we need to do 1 left shift count plus 1, right? This value we need to do left. Oh, is it left plus this value? It's not left plus this value. It is left plus. Hold on. It's a left plus this value. It's not left plus this value. It's the mask. Right, it's the mask plus this value. So we need a mask. High is this. Low is left. Rest is left. And we need a mask. Mask is equal to 1 left shift length this. Right? So if it's 1, 2, 3, 4, 5, 6, 7, so it's shift 7. 1, 2, 3, 4, 5, 6, 7. No, shift too much. So this is going to be minus 1. So that is the mask. So we're going to say if this is going to be the mask plus this, but that will be smaller. That will be smaller. Huh. How do we express this? I want 1, 0, 0, 1, 0, 1, 0, right? And then next one, I want 1, 0, 1, 0, 0, 0, 0, right? So it's going to be if we left shift, right, and then we have this. Hold on. We might be able to use the right shift to do this. So we have 1, 0, 0, 1, 0, 0, 1. And then first place is, then what? And then what we're going to say is we need to turn this, right? Oh, maybe we can end it. We end, oh, no, not end. This is a 1, right? So all we need is to, and it's not exclusive or, and everything becomes 0, and then we need to hold up. It's going to be we end it and then or it. We end with what? Hold on. So we have this position, right? So we have this position, and then we need to discard this, right? We need to discard this. How do we discard this? Oh, we need to know how many positions we have, right? So 1, when you say 1 left shift 0, and we're going to do exclusive OR, which will turn the end into a 0, and then 1 left shift 1, and then that one's gonna add to it. Okay, so for the next, it's going to be the same. So we're gonna left shift this much, exclusive OR it, so we can turn the 1 into a 0, and then end with 1. Okay, I think this is how I'm going to do. So it's so convoluted though. It's not mask. It's not mask. So we're gonna have so we're not gonna do mask. So we're gonna say the target, right? So whenever we find it, when we find a target, see if it is smaller or it is bigger. So what we're gonna have is a target is going to be left exclusive OR 1 left shift count, right? 1 left shift count. So when the exclusive OR this, that will take the this position into a 0, right? That's what we want. And then we're gonna, the entire thing is going to end 1 left shift count plus 1. And that will turn, so we're going to turn this position to 0, and we don't care about the rest. And then we're going to end, so we'll put this position into a 1. So that is the smallest value based on the current left that will have this position as 0, right? This position is 0. So we need to see if this value is included, right? Now, if this value is included so that because if this value is included, is within the limit, then this position will be 0, right? This position will be 0. Now, if this position will be 0, and then we need to keep going. And if this value is not included, right, then we are done because we will not hit this value be included. So it will just be whatever it is. Okay, so target is this, and we just say if target is included, which means it's smaller equal to high, right? If it's included, then If it's included, then I need to change the result, right? It's included, we need to change the result, which means res is going to be exclusive or equal 1 left shift count, right? So that's, wait, is it exclusive or 1 left shift count? Yeah, because everything else will be all 0, so it's fine. So exclusive, so just turn that 1 into a 0, right? And then we continue. All right, and then this is this. If left is smaller, else, then we break, right? Else, if the target is larger, is not in high, then that one will never be handled, and then we're done. So if this is going to be this, otherwise, just a low right shift equal 1. So we always keep right shifting, and every time right shift counter be incrementing, and eventually we return res. All right, so what can we do to make this high? We use high. Binary left, we use only once, so I can just put this one here. So high, and then we can say low, res, and a count equals left, and 0, right? And now I say while low, if the rightmost is a 1, we calculate a target, right? And the target, if the target is small, actually we don't need a target because we can just do this. Calculate the target. If the target is smaller than high, then we need to turn the current into a 0. If the target is larger than high, that means there's no need to keep going, then we break. And otherwise, we keep right shift low until we hit. All right, let's try this. It's actually not. It's not complicated, but it's a little bit complex, I would say. 5, 7 will be 4, right? And I'm not very confident in this. And 1, whatever this value. That's why I think it's this value. This and this one give us 0, right? So left, right, range. Oh, what do you do, man? Range this left, right. Uh-oh. First one is not right. The result is 0. Answer is 4. Okay, so high. So I got it. So the result shall be 4, right? Why would be 0? So the high, let's print out high. High is definitely, high shall be 7, right? So we print high. High is 7, that's good. And then every time I just need to print out the binary of this. So it's binary of this, right? So this is going to be the every time. So we just print binary of this. Oh, so something wrong with here. All right. So count is 0. This is 1, right? Left. Why would it be 0? Because this is not AND. This is not AND. What is it? So I exclusive OR. I turn that into a 0, okay? And then if I AND this, then everything is 0. Why would it be 0? Left 1 left shift is 0, so exclusive will be 1 0 0, right? And this one will be left shift 2 times, right? So 2 times. No, it's 1 time. Count is 0. Start with 0. So left shift once, and then we need to see, all right, we need to see if it's, and I say n. No, that's not n, but still, this one shall give me, low is left, low and 1. Yeah, that should turn 1. Hold on. Low. Low is 5. Yeah. Low is 5. And then let's print binary. Yeah, let's just binary the whole thing. So left exclusive for 1. That shall give me 1 0 0. That's what I expect. 1 0 0. Binary this. Okay, so 1 0 0. That is correct. And then it's 1 0 0, and I need to. But it's exclusive OR. It's not exclusive OR. So what we want is we can end it, so we can move everything to be 0, right? And just clear out the remaining. Do we need to do that? Maybe it could be a result, because the result is cleaning, right? So like if this, I'm cleaning. Yeah, I think it's result, because the result, the remaining is all 0. I'm cleaning here, and that's, but that's only exclusive OR. I need to clean the remaining. So exclusive OR becomes 0. That's fine. Result is going to be all 0 for the remainder if we just swap those ones, right? We swap those ones. The result is fine. So we can use a result. And then for the result, all we need to know is if the result, we flip that, and yeah, so we can try this. Let's try this. Low, right? We don't use left. We use result, exclusive OR, this will give us that, and so we can use result, exclusive OR, and this is going to be OR. So we need to put 1 there, so we turn the current bit into 0, and we add a new bit to the left. And if this, then we say we turn this bit into 0, all right? Yeah, and then we keep going. And then low right shift. Yeah, so let's try this one. Now we pass. Now that is going to be OR. And then the other one, the heck, the last one failed. That's strange. Why would the last one fail? 1, right? And then hold on. It's complicated than I thought. If it's 1, and then my saying is it's going to be determined by, I see. Now this is, interesting. No, I think this is the wrong way. So in total, we have 31 positions, right? Let's think a different way. So we have 31 positions. The question is, from the start to end, will some position remain 1, right? That's the question. So we have a starting point, whatever value, and then we have an end point, right? Whatever value is on the endpoint. So the question is, within these, would it be possible that some value becomes 1? So we have a starting point and we have an end point. And we know anything to the left of the starting point, these are going to be 0. So these we do not care. So now we care about the rest. And then we want to know if any position will become, or like if it's a 0. Okay, if it's a 0, then definitely will be 0. So the start and end, right? We're going to do a start and end the end, right? And then, how should I put it? Man, this is a simple question, man. So whatever it is 0, right, is no. So in the starting point, the left, we can find whatever ones. And then in the end point, if we remove the front, then we know there gotta be 1, right? Starting with 1, 1, 1, 1, 1, right? That's the thing. And then it's in between. So if it's this, then we know there gotta be someone that says this is a 1. But we're ignoring the fact that there could be zeros in those positions. The question is, will we have zeros in those positions? So we ask whether it would be 0 in this position. I only consider the value smaller, but it actually can be bigger. It can also have 0 position in those. So what? So if it's a 0, right? We can say if it's a 0 and then what? Like the smallest value. Yeah, it should be the smallest value with this is 0. So it's going to be this, right? All 0. We should say if this one is the smallest value that can make this. Okay, I think I changed my mind. Come back here, all right? So we have this. So what we need to check, this is the starting point, right? So what we need to check is if there's a value that can have this one as a 0, right? Which is the smallest value that can have this one as a 0, or this one is a 0, smallest value that's bigger than this. It's bigger than this, that can have the smallest value that can have this is a 0. So the smallest value that can have this as 0 is going to be, but we shouldn't set an upper bound. I think that is the problem. We should not set upper bound. There's no point to set an upper bound. Like this high, there's no point. It shall be just right. Right? This is just right. So we are analyzing the left. Right? We're analyzing the left. And in this case, we don't even need a low. Right? We don't need a low. We can just go left. Low is left. Low is left. And then we just go left one by one, right? And just check for each one, can we create a value that's bigger than left, which is what we're doing here. That's bigger than left, but it's smaller than right. If we can create a value bigger than left, smaller than right, with that position being 0, then that one needs to be turned into 0, right? Otherwise, we escape. Right, so that's my answer. I mean, I can actually go a little bit more. It's an easy template. I don't know, I can do like random stuff. Test case will be interesting to write. Right? So we can run code and just see how it goes. Yep, I think we're good. It says accepted, which means I think all of them are good. Let's try it. Submit. ending. Oh, got wrong answer. Jeez. Output 2, expected 3. How does that happen? How does that happen? Man, this is such a simple question. I got stuck. Yep, this one is wrong. 3, so 1, 1, right? So 1, 1, 1, 1. I should check this myself. So while left, and the first one is a 1, right? And then we say res, the smallest one. What I do is I turn this 1 into a 0, right? And then I OR it. Maybe you should not OR it. You should plus. Plus. Wait, really? Plus? I mean, if it's like all zeros and then we do this and we do plus, that's the same thing, right? But if it's a 1, right? If it's adjacent, if 1's a 1, if this 1 has adjacent 1 in front of it, then if we OR it, that value is actually be smaller, right? And that's wrong. That just means if I have 1, 1, the smallest value that can make the first one become 0 is 1, 0, 0. So if we do plus, that will pass. All right, so I'm going to change this into a plus. Actually, I want to change counting to C, so I can make this a little shorter. Make it a little bit shorter. And then I want to run more test case. Yeah, this time we run more test case. 3, 3, no, what, like 7, 7, right? What's the next one? 7, 31, 31, 31. And gibberish, gibberish. Try it. It's correct. 731. And actually, if left equals right, then we can return it immediately. We don't have to go through this. Okay, like special case, right? Special case, if left equals right, then but this one, yeah, but if you don't do it, it's gonna have to go many times, right? So I just say if left is equals to right, then we just return left. I mean, this one still works, but I think this probably will be better. All right, try again. There you go. Oh, it was slow, only 40%. 464 days. Okay, so let's check the solution. Let's write something first. It's surprising it took so long. Yeah, this is not a hard question, so I feel bad. I feel bad that it took so long. It's basically bit manipulation. We know that we know that any bits in any value, right, larger than left with more bits on the left side don't matter, right? Therefore, all we need to check is whether the ones in left can be maintained. To do so, we need to find where the one bits are in left and create a value, create the smallest value that will have that 1 bit position or have 0 at that 1 bit position. If this smallest value is within range, now we know the 1 bit in left cannot be maintained. Otherwise, we can stop searching because all the rest of the 1 bit, all the rest of the 1 bits at higher positions can be maintained. Now, I'm not even sure this makes any sense. For instance, given left equals 1, 0, 0, 1, 0, 0, 1, to check for the rightmost 1 bit, we need to see whether 1, 0, 0, 1, 0, 1, 0 is within range. To check for the second rightmost 1 bit, we need to see whether 1, 0, 1, 0, 0, 0, 0 is within range. Therefore, the algo is basically to figure out how to acquire the value for checking, right? For checking. And our runtime, we call it O1 because there's a I call it O1. I call it 1 because there are at most 31 positions to check in the loop. But our runtime is pretty bad, 72 milliseconds, only 40%. We're gonna see how the distribution is. Maybe it's not that bad. But we did got it wrong once. That's very disconcerting. Alright, let's see. Good at 56. Oh, very simple. This is interesting. If right is large or equal to left times 2. Ah, yes. That is good. That is good. Check. Oh, then we... Oh my goodness. Oh my goodness, this is good. And then we're only doing from left to right. Holy guacamole, this is good. Because we are saying we are reducing, so if it's larger, then we don't consider. So we only consider from right to from left to smaller than double of the left. Right? So any value we double it, and then within we can do. Oh, this is good. I mean, it's simple, right? It's simple. We're talking about simple solutions. Super simple. Different. Yeah, they all do a range. Right, maybe we can upload our solution. Oh, log in. Binary length of number is different, then the answer is equal to 0. If lengths are equal. Oh, if binary length is different. How did I not see that? If the binary length is different. Yeah, I didn't see that. So we are stuck with if lengths are equal, we remove the first symbol, which is 1, and do recursions. For two binary numbers, the answer will be the common prefix. If this or this, return m. If length is not the same, then return 0. That's true. And then it's going to be 1 left shift m. So a left shift that much, and then we see we're removing the leftmost one bit, and then that's going to be exclusive OR the remaining. Huh. Now I'm checking one by one, but that is correct. If the length is not the same, I didn't think about that. If the lengths are not the same, yes, if the lengths are not the same, okay. So now we are handling lengths are the same. So if the lengths are the same, then we just need to check one by one at all the 1 bit. I mean, some solutions just if lengths are the same, then we just go through everything. I mean, that's definitely one solution. We can just go through everything, which is fine. We just go through everything. Not too many to calculate. But we can do better, right? So I can do this, right? But, yes, the number of bits are not the same, then it's a 0. Now the number of bits are the same, all right? So we're gonna go one by one. We pick the first one. Now I still think we can go looking at the left. Yeah, I will still use the same method, right? I will still use the same method, but I'll tweak the right. And now we just go through a fewer number of bits. It's going to be plus, yes. I'll have a result from the left. So I think what I will do is change this, right? So if they're equal, then return left. Then if len binary left is not equal to len binary right, then return 0. So these two are the beginning, right? These are the beginning, and they can eliminate a lot of situations. Now we are handling the left and right of the same length, but I don't care. All I care about is go through left one by one, and I will check whether each one can be will be turned into 0 by finding the smallest value, right, that can make it into a 0. And now we check if it's okay. That is an upgraded version. I think this one will still work. So I say this is upgraded. So update. from reading the discussion, it is clear that if the number of bits in left and right are not the same, the result must be 0. Yeah, I should have realized this. So the updated version, add a version below, the version adds this extra check, which can reduce quite a few computation. That's what I think. So I'm going to run this and see how this one goes. Everything else will be the same, right? Everything else will be the same. Interesting. Now, the method that he used is recursion, which is understandable, right? Which is understandable. Recursion seems to be a good way of handling this, but let's try this. Let's try this. 48. See, immediately we go to 48. Go to 48. So this one goes to 48 milliseconds, or it becomes 96% ranking. I think I'm gonna post this. But for the recursion idea. So recursion idea is, say, if at a certain position, right, both have 1, then the result will be 1, right? And then I remove this, so for the remaining value, so we check if, right, we check the remaining value, and then, hold on, what we're removing is, so removing, no, we're still looking at the left, right? We're looking at the left, and then we are going to remove that, okay? And then remove that, the prefix, remove the prefix on the right as well, right? We remove the prefix on the right as well. And then after remove the prefix, we have the remainder. And I'm going to do same on the remainder, okay? And whether the prefix can exist depends on the remainders, right? So the prefix, whether the prefix can exist depends on the not really depends on the remainder. So like every function call, this is recursion, every function call will determine the result, right, of the result. And all we need to do is, for each function, we pick out the leftmost bit on the left, right? The leftmost bit on the left. The leftmost bit on the left, and then that will be the prefix. That will be the potential prefix. And then we're going to pick out the right. So minus that. Right? Minus that. Why do we minus that? Because all the things in the middle, they're all 0. They don't care, right? So if this one minus that, we minus the leftmost bit, and then the remaining, yes, because every time for the left we remove, the right also remove the same amount, right? So that will be the new comparison, left and right. the new comparison. We need to remove that same because that one, yeah, that's the part that we don't consider. So it's the same idea, but with better implementation, the easier implementation. Let's try this. So this one is from the Bobby Chef. I'm gonna put a link later. So the idea is that for any given left-right pair, right? Any given left and right pair, we return 0 if they are the number of bits in them are different. If they are the same, that means the highest one bit can be maintained. Yeah, that means the highest one bit can be maintained. Thus, we search for the second highest bit in left and perform the same. We reduce left to the second highest bit, right? The second highest bit, and reduce the same amount on right as well, and then recurse. So I'm going to say if left equals right, if left equals right, then we return left. So if the two are the same, we always return. And then if these are not the same, then we return 0, right? So this is good. Otherwise, then we know we just need to get the leftmost bit, right? So to get leftmost, like a prefix equal to the leftmost bit. Leftmost bit equal to 1 left shift len bin left. We need a -2 is total, but that will be too much, so we need a -3. Right, so -3, that gives us the leftmost bit value. So we're going to return this. I think OR is fine. We're going to OR self.range. That's going to be left minus this. We take that away. So it's remaining of the left. And to compare, we have to take out exactly the same on the right. The right minus this. So solution 2. Very good. Oh, let me add the reference as well. I like this one. Oh, I just see it also has a little bit better. So if this equals this, I'll return or if right is 0. So if the starting, it doesn't matter if right is 0, this is going to be 0. If any one of these is going to be 0, so I don't think we need that check. So yeah, this is a good one. This is a very good one. I think this one will give us a good result as well. Submit. Oh, that's why. That's why he added that one. Why would this fail? That's a no. That's a no because they have the same length. And then one left shift. Oh, there's no 1 in this. There's no 1 in this. That's a 0. 0, 1 should be 0. Yeah. Left not equal to right. And then these are not the same. They're the same, right? So we're gonna do, this is gonna be what? Len bin, well, that's only one, so 0, so shift to 1, shift to 0, right? So it's gonna be 1. So left minus 1 is a negative value. Ah, that's not good. So if left equals right, or left equal to 0, then we return left. That's why you need this. Or left equals 0. That's why you need this to handle this situation. There we go. Okay, so I think let me post mine. Right, that definitely will do some change. So what do we call it? 3. Find the smallest value bigger than left that can make the 1 bit in left turn 0. Wow, that's a long title. Find the value, right? Find the value that can make the 1 bit in left become 0. Okay? I want to copy and paste this whole thing and then make some changes in the comments. Alright. Oh, that's not what we want. Forgot to do this. Alright, so yeah, I just close this way. It's fine. Add this extra check, which reduces quite a bit computation. Yeah. All right, but from simplicity wise, this one is simple. This one's simple to write and also pretty fast. All right, that will be it for today. I will see you guys tomorrow. Adios.